Today's topic is transformation of electromagnetic vector potential A and scalar potential phi. Transformation of electromagnetic potentials A and phi. A is vector potential and phi is scalar potential. And we will define 4 vector potential. Lorentz condition is given by this equation: del vector dot A vector plus mu 0 epsilon 0 delta phi upon delta t. A vector is vector potential and phi is scalar potential, and Lorentz condition relates these two potentials by this equation. This equation suggests that we can define a 4 vector A mu as A mu equal to A vector I phi upon C, and this 4 vector A mu is 4 vector potential. First 3 components are components of A vector, components of vector potential A vector, and 4th component is related to scalar potential phi, and this 4th component is I phi upon C. So 4 vector potential A mu is equal to A vector and I phi upon C. To prove that A mu is a 4 vector, let us consider Maxwell's field equations. There are 4 Maxwell equations, and in terms of vector and scalar potentials, these 4 equations reduces to these 2 equations. First is for vector potential A, and second is for scalar potential phi. Del square A, del square here is D'Alembertian. First equation is del square A equal to minus mu 0 j, and second equation is del square phi equal to minus rho upon epsilon 0. This equation 4, del square phi equal to minus rho upon epsilon 0, can be written as del square I phi upon C equal to minus I upon C rho upon epsilon 0, multiplying by I upon C on both sides. Right hand side then becomes equal to minus IC upon C square rho upon epsilon 0, multiplying and dividing by C. C is the speed of light, so that in denominator we have C square, and value of C square is equal to 1 upon mu 0 epsilon 0. So right hand side now becomes equal to minus IC mu 0 epsilon 0 rho upon epsilon 0, and it is equal to minus mu 0 IC rho, where IC rho is J4, 4th component of current 4 vector. Here we have used C square equal to 1 upon mu 0 epsilon 0. Now this equation 4 now becomes del square A4 equal to minus mu 0 J4, while equation 3 is del square A equal to minus mu 0 J. These two equations, equation 3 and equation 5, are combined together to form this equation del square A mu equal to minus mu 0 J mu. First three components are in this equation 3 del square A equal to minus mu 0 J, while fourth equation is in this equation 5 del square A4 equal to minus mu 0 J4. These two equations 3 and 5 now becomes del square A mu equal to minus mu 0 J mu. As del square, which is D'Alembertian and it is Lorentz invariant, in right hand side J mu is current 4 vector, so it is clear that A mu must be equal to a 4 vector, and this 4 vector A mu is known as 4 vector potential or electromagnetic 4 potential. Now A mu is a 4 vector potential or electromagnetic 4 potential. It must transform under Lorentz transformation according to A mu dash equal to alpha mu nu A nu. A mu dash is written as column matrix having 4 components A1 dash, A2 dash, A3 dash and A4 dash. Alpha mu nu is this square matrix, 4 by 4 square matrix, and A nu is a column matrix having 4 components A1, A2, A3, A4. From this metric equation we can find 4 equations. First equation is A1 dash equal to gamma A1 plus I gamma beta A4. Gamma is taken common, so it becomes gamma A1 plus I beta A4. Substituting the values of beta and A4, beta is equal to V upon C and A4, fourth component of this 4 vector potential, is I phi upon C. If we substitute values of beta and A4, we have this A1 dash equal to gamma A1 plus I V upon C I phi upon C, which becomes equal to gamma A1 in gamma into A1 minus V upon C square phi. Similarly, other equations are A2 dash equal to A2, A3 dash equal to A3, and fourth equation is A4 dash equal to minus I gamma beta A1 plus gamma A4. Gamma is taken common, gamma into A4 minus I beta A1. Now in this equation we substitute the values of A4 and A4 dash. A4 is fourth component of 4 vector potential. It is I phi upon C, while A4 dash is equal to I phi dash upon C. Substituting these two values, this equation reduces to this equation I phi dash upon C equal to gamma I phi upon C minus I V upon C A1. V upon C is put for beta. So from this equation we can find an equation for phi dash. To obtain equation for phi dash, we have to eliminate I by C from left hand side. So we must multiply this equation by C upon I, and we get phi dash equal to gamma phi minus V A1. So we have these 4 equations, and these 4 equations are the transformation equations for A vector and phi. Transformation equations for 4 vector potential. Lorentz condition in covariant form. Lorentz condition is this: del dot A plus 1 upon C square delta phi upon delta T. This can be written as del dot A plus delta I phi upon C upon delta ICT. In the second term of left hand side, we multiply phi by I upon C. We multiply the second term of left hand side by I upon C, and also we divide this term by I upon C. So in numerator we have I phi upon C in place of phi, and in denominator we have ICT, so that I phi upon C becomes A4, fourth component of vector potential, 4 vector potential, and in denominator we have ICT, which is x4, fourth component of position 4 vector. Del vector dot A vector is equal to delta A1 upon delta x1 plus delta A2 upon delta x2 plus delta A3 upon delta x3, and this second term becomes delta A4 upon delta x4. So Lorentz condition now reduces to this equation: delta A1 upon delta x1 plus delta A2 upon delta x2 plus delta A3 upon delta x3 plus delta A4 upon delta x4 equal to 0. This left hand side can be written as delta A mu upon delta x mu equal to 0. Here summation is for mu, and values of mu varies from 1 to 4. Values of mu are 1, 2, 3, 4, and summation is for mu. Or we can write it as del dot A mu equal to 0. Here del in a square form is 4-dimensional differential operator. So this is the covariant form of Lorentz condition: delta A mu upon delta x mu equal to 0, or del dot A mu equal to 0. Next topic is the electromagnetic field tensor. The electromagnetic field vectors E vector and B vector, electric field E and magnetic field B, are written in terms of electromagnetic potentials A and phi as: electric field vector E vector and magnetic field vector B vector are related to A vector and phi by these two equations: B equal to del cross A and E equal to minus del phi minus delta A upon delta T. From first equation, which is B equal to del cross A is equal to this determinant. In first row we have I cap, j cap, k cap, 3 unit vectors. In second row we have 3 components of del vector, that are delta upon delta x, delta upon delta y, delta upon delta z, and in third row we have 3 components of A vector, that are ax, ay, az. Now In left hand side, B vector can be written in terms of its components as Bxi plus Byj plus Bzk. Bx, By, Bz. These three are three components of B vector along the directions of x-axis, y-axis and z-axis respectively. And right hand side, in right hand side we simplify this determinant and get I cap delta Az upon delta y minus delta Ay upon delta z plus j cap delta Ax upon delta z minus delta Az upon delta x plus k cap delta Ay upon delta x minus delta Ax upon delta y. Now, by comparing the coefficients of I cap, j cap and k cap, we get these three equations. Bx equal to delta Az upon delta y minus delta Ay upon delta z, which can be written as equal to delta A3 upon delta x2 minus delta A2 upon delta x3. Similarly for By and Bz. From equation 2, which is E vector equal to minus del phi minus delta A upon delta t, we can write its three components Ex, Ey and Ez as Ex equal to minus delta phi upon delta x minus delta Ax upon delta t. Its first component, x component of equation 2, x component of E vector is Ex, while x component of del phi is minus del x component of del phi is delta phi upon delta x, and x component of delta A upon delta t is delta Ax upon delta t. Similarly, we can write for Ey and Ez, and these three equations for Ex, Ey and Ez can be written as these three equations by multiplying by I upon C on both sides. If we multiply by I upon C on both sides of these three equations, we have I Ex upon C equal to minus delta upon delta x I phi upon C plus delta Ax upon delta ICT. By multiplying by I upon C on both sides, in right hand side we get these two terms which are I phi upon C, which is A4, fourth component of A mu for vector potential, and the other is ICT, which is X4, fourth component of X mu, position for vector. So this equation becomes I Ex upon C equal to minus delta A4 upon delta X1 plus delta A1 upon delta X4. Similarly, other two equations are I Ey upon C equal to minus delta A4 upon delta X2 plus delta A2 upon delta X4, and I Ez upon C equal to minus delta A4 upon delta X3 plus delta A3 upon delta X4. Equations 3 to 8 can be expressed as, if we combined all these equations from equation 3 to equation 8, all these equations can be combined by this single equation, F mu nu equal to delta A nu upon delta X mu minus delta A mu upon delta x nu. With F23 equal to Bx, F31 equal to By, F12 equal to Bz, F41 equal to Iex upon C, F42 equal to Iey upon C, F43 equal to Iez upon C. And also F mu nu equal to minus F nu mu, and F mu mu equal to 0. This F mu nu have 16 components, and it is written in matrix form by this equation. These are the 16 components: F11, F12, F13, F14 in first row, F21, F22, F23, F24 in second row, F31, F32, F33, F34 in third row, and F41, F42, F43, F44 in fourth row. F mu nu having these 16 components expressed by 4 by 4 matrix. This F mu nu have these 16 components. And this F mu nu is known as electromagnetic tensor of rank 2. This is known as electromagnetic field tensor F mu nu having 16 components related to 3 components of electric field E vector, that are Ex, Ey, Ez, and 3 components of magnetic field vector B vector, that are Bx, By, Bz. So F mu nu electromagnetic field tensor is given by this equation: F mu nu equal to delta A nu upon delta x mu minus delta A mu upon delta x nu, and this tensor have these 16 components written by 4 by 4 matrix. Now we write Maxwell's equations in covariance for tensor form. These are the 4 Maxwell's equations in a region of charge density rho and current density J. Del dot E equal to rho upon epsilon 0, del dot B equal to 0, del cross E equal to minus delta B upon delta T, and del cross B equal to mu 0 J plus epsilon 0 delta E upon delta T. Here epsilon 0 and mu 0 are permittivity and permeability for free space. 0 is used for free space, epsilon 0 is permittivity, and mu 0 is permeability. Rho is charge density and J vector is current density. Introducing the coordinates x equal to x1, y equal to x2, z equal to x3, and ICT equal to x4, Maxwell's field equations may be written as. For these 4 Maxwell's equations can now be written as: first equation, del dot E equal to rho upon epsilon 0 can be written as delta Ex upon delta x1 plus delta Ey upon delta x2 plus delta Ez upon delta x3 equal to rho upon epsilon 0. Second equation, del dot B equal to 0 can be written as delta Bx upon delta x1 plus delta By upon delta x2 plus delta Bz upon delta x3 equal to 0. And third equation, del cross E equal to minus delta B upon delta T can be written as I cap delta Ez upon delta x2 minus delta Ey upon delta x3 plus j cap delta Ex upon delta x3 minus delta Ez upon delta x1 plus k cap delta Ey upon delta x1 minus delta Ex upon delta x2 equal to minus delta upon delta T I cap Bx plus j cap By plus k cap Bz. Left hand side of this equation can be obtained by solving for del cross E by using determinant method. Similarly, fourth equation can be written as I cap delta Bz upon delta x2 minus delta By upon delta x3 plus j cap delta Bx upon delta x3 minus delta Bz upon delta x1 plus k cap delta By upon delta x1 minus delta Bx upon delta x1 equal to mu 0 I cap j1 plus j cap j2 plus k cap j3 plus mu 0 epsilon 0 I cap delta Ex upon delta T plus j cap delta Ey upon delta T plus k cap delta Ez upon delta T. Right hand side of this fourth equation is equal to mu 0 I cap j1 plus j cap j2 plus k cap j3 plus I upon C I cap delta Ex upon delta x4 plus j cap delta Ey upon delta x4 plus k cap delta Ez upon delta x4. So here in second term of right hand side we have used the relation that mu 0 epsilon 0 is equal to 1 upon c square. C is speed of light and speed of light c is equal to 1 upon under root mu 0 epsilon 0. So 1 upon c square is equal to mu 0 epsilon 0. So in the second term for mu 0 epsilon 0 we write as it is equal to 1 upon c square, and where there is term of delta t in denominator we multiply by IC so that ICT becomes x4. We multiply the denominator by IC, so we have to multiply the numerator by IC. So multiply and divide by IC, and ICT, for ICT we write x4. So second term in right hand side becomes as equal to I upon C into I cap delta Ex upon delta x4 plus j cap delta Ey upon delta x4 plus k cap delta Ez upon delta x4. From equation 8 we have this is equation 8, last equation. delta bz upon delta x2 minus delta by upon delta x3 equal to mu 0 j1 plus I by c delta ex upon delta x4, delta bx upon delta x3 minus delta bz upon delta x1 equal to mu 0 j2 plus I upon c delta ey upon delta x4, and delta by upon delta x1 minus delta bx upon delta x2 equal to mu 0 j3 plus I upon c delta ez upon delta x4. We have these three equations from equation 8. By comparing the coefficients of I cap, j cap and k cap on left hand side and right hand side, these three equations so obtained can now be written as: first equation can be written as 0 plus delta bz upon delta x2 minus delta by upon delta x3 minus I upon c delta ex upon delta x4 equal to mu 0 j1. We write mu 0 j1 term on right hand side only, and the other term in right hand side is taken to the left hand side. And in left hand side, now we write the terms in this order: delta upon delta x1, delta upon delta x2, delta upon delta x3 and delta upon delta x4. There is no term for delta upon delta x1, so we write 0 for this term. Similarly, other two equations can be written as minus delta bz upon delta x1 plus 0 plus delta bx upon delta x3 minus I upon c delta ey upon delta x4 equal to mu 0 j2, and delta by upon delta x1 minus delta bx upon delta x2 plus 0 minus I upon c delta ez upon delta x4 equal to mu 0 j3. These three equations can be written in terms of f mu nu, electromagnetic field tensor, as these three equations: 0 plus delta f12 upon delta x2 minus delta f13 upon delta x3 plus delta f14 upon delta x4 equal to mu 0 j1. Second equation becomes delta f21 upon delta x1 plus 0 plus delta f23 upon delta x3 plus delta f24 upon delta x4 equal to mu 0 j2, and last one is delta f31 upon delta x1 minus delta f32 upon delta x2 plus 0 plus delta f34 upon delta x4 equal to mu 0 j3. Here we see that in this equation for bz, second term of left hand side, for bz we have written f12. For by in third term we have written as f13, and in fourth term of left hand side we write f14 for minus I ex upon c. These terms can be obtained from this tensor f mu nu, which is equal to this 4 by 4 matrix. All values of components of f mu nu can be obtained from this matrix. So we now get these three equations 9, 10, 11, and from equation 5 is this delta Ex upon delta x1 plus delta Ey upon delta x2 plus delta Ez upon delta x3 equal to rho upon epsilon 0. This is equation 5. From this equation we can write I by C delta Ex upon delta x1 plus I by C delta Ey upon delta x2 plus I by C delta Ez upon delta x3 equal to I rho by C upon epsilon 0. Multiplying that equation 5 by I by C. Right hand side now reduces to equal to I rho C upon C square epsilon 0, and C square is equal to 1 upon mu 0 epsilon 0. So right hand side of this equation becomes mu 0 J4. Here we have used C square equal to 1 upon mu 0 epsilon 0, and J4 is I0. This equation can be written as, in terms of electromagnetic field tensor F mu nu, this equation can be written as delta upon delta x1 delta F41 upon delta x1 plus delta F42 upon delta x2 plus delta F43 upon delta x2 plus delta F44 upon delta x4 equal to mu 0 J4. Equations 9, 10, 11, 12 can be written by a single equation, delta summation delta F mu nu upon delta x nu equal to mu 0 J mu. In left hand side, the summation is for nu because nu is index which is repeated, it is 2 times. So in left hand side, summation is for nu, and summation delta F mu nu upon delta x nu equal to mu 0 J mu. Here F mu nu is electromagnetic field tensor given by this 4 by 4 matrix. Similarly, from equation 7 we can write these three equations, and these three equations can be written by as these three equations. We can write these equations as these three equations can be written as these three equations 15, 16, 17. And from equation 6 we have delta F23 upon delta x1 plus delta F31 upon delta x2 plus delta F12 upon delta x3 plus 0 equal to 0. These 4 equations 15, 16, 17 and 18, these three equations 15, 16, 17 and this is equation 18. These 4 equations can be combined by this single equation, which is delta F mu nu upon delta x lambda plus delta F nu lambda upon delta x mu plus delta F lambda mu upon delta x nu equal to 0. Equations 13 and 19 represent Maxwell's field equations in terms of electromagnetic field tensor F mu nu. Maxwell's equations in terms of electromagnetic field tensor F mu nu can be written by these two equations. First is this, summation delta f mu nu upon delta x nu equal to mu 0 j nu. Here in left hand side summation is for nu, which is repeated index, and the second equation is this delta f mu nu upon delta x lambda plus delta f nu lambda upon delta x mu plus delta f lambda mu upon delta x nu equal to 0. These two equations represent Maxwell's field equations, and these are in terms of f mu nu, which is electromagnetic field tensor.